So, in that video we saw that the magnet, which is free to spin around, is acting like a compass needle, orienting itself with whatever is producing a magnetic field nearby. Since there were no other magnets nearby, it must be reading, or sort of reacting to Earth's magnetic field. So the Earth acts as if it has a giant bar magnet inside of it. And so that magnet that was free to spin around inside the bowl of water had its north pole oriented to point north. Wait a second. Why would the north pole be attracted to north? Because north is attracted to south, right? Okay, so this is where it gets a little bit weird, right? And so a north pole of a magnet is attracted to this end of the Earth. That means that over here must be the south magnetic pole, and over here must be the north magnetic pole. So it turns out the Earth actually acts as if it has a giant bar magnet inside of it, which looks like this. Ah, okay. So, based on this, I want you to pause the video. I want you to draw Earth's magnetic field based on the rules we just went over in the previous video. Okay, so here's a slightly different view of it with some professionally drawn magnetic field lines. And so if the north pole is over here and the south pole is over here, magnetic field lines come out of north and they loop around to go into the south. They continue inside the magnet itself, in this case, inside the Earth. Alright, so this is what you should have drawn, something that looks sort of like this. Alright, so what about this confusing bit here? Should this change everything? Well, no. Here's the idea, is that the north pole of a compass is attracted this way. That means that must be the south magnetic pole of the Earth. So however, that's what we call Earth's north pole. We just call that Earth's geographic north pole. And over here is the magnetic north pole, but that's Earth's south geographic pole. So, this shouldn't change anything about how you view things. If you're looking at a globe, over here is the North Pole. That's where Santa lives, and over here is the South Pole, where the penguins live. But it's just really a matter of how we name it. So, if you're looking at a compass and you want to go north, you follow whichever way the North Pole points. Okay, that's the idea. The North Pole of a compass points to magnetic south. We call that geographic north. You're following the North Pole of a compass to go north. Okay, so this shouldn't change anything about your worldview. It's not like you get some driving directions and it says to go north, and you say, facing north is, oh, we got to turn around and go the other way because I'm reading it wrong. That's not how it works. In fact, you won't end up where you belong. All right, it's really just a matter of naming it. Now, we don't know why the Earth has this magnetic field. There's all sorts of theories as to what's going on inside the core of the Earth, although we can't actually get there. Right? We discussed that earlier in the year when we tried to dig our tunnel through the Earth. We wouldn't survive the trip. But there's all sorts of theories of what's going on there where we create a magnetic field. And the magnetic field does exist inside the Earth itself. This is why we draw our field lines inside. So if you dig down deep enough, you actually find, you can pull up some naturally magnetic materials and you'll see it aligns itself with Earth's magnetic field. What's interesting, though, is if you dig deep enough and you pull out rocks that formed more than 70,000 years ago, which shows that Earth's field used to be aligned the other way. And about 70,000 years ago, it reoriented itself to its current configuration. And if you dig even deeper than that, we find that it's happened many times over Earth's history, that the poles flip positions every once in a while, and it seems to happen with some sort of periodic nature. In fact, we seem to be overdue for a flip. And so if you were ever lost in the woods and you're following a compass needle and just all of a sudden it flips around the other way, you say, oh, it was today. Again, it doesn't really change anything about your worldview, but just be aware it does happen. We don't know why it happens, but also we don't really know why Earth has a magnetic field. So just par for the course. All right, let's get into some more problems here. So back into our problem set, let's take a look at number 3, where here I want you to do all the math for problem 3, parts A, B, C, and D. Don't worry about the direction of the magnetic force. We'll come back and we'll practice some right-hand rule. So anytime we have these pictures here, it's blue on my screen here, but you have black on your paper. But there's a B there indicating that this is the magnetic field. So all three of these lines are indicating that maybe there's like a uniform magnetic field produced by some strong laboratory magnet, and the field lines are pointing to the right. And here we have a positive point charge moving at the same speed but at different orientations with respect to the magnetic field. Clearly, of course, we're using the equation F sub m equals QVB sine theta, and the charge is given, but it's given in microcoulombs. I hope you caught that, right? Of course, micro 10 to the -6, and the velocity is there, the field strength is there. And for this first one, the angle is 90 degrees, real simple. So you put your numbers in, and you should be getting 0.32 newtons. It's obviously a 2 sig fig problem. You shouldn't have any problem here, just plug and chug. For B, C, and D, we're doing the same sort of thing over and over, and hopefully you've recognized the pattern, how we do this throughout the year, right? Yes, I'm a big stickler for you showing all your work, but if we're really just doing the exact same thing, I hope you did not waste any of your time showing all your work. All you're doing is changing the angles. You should have no problem just doing that, and we should be getting 0.23 newtons for B, 0.16 newtons for C, and then 0 newtons for D, which is interesting. So we'll come back to talk about that. But right now let's talk about the right-hand rule for the direction, because this equation just gets you the magnitude. And in fact, we take the absolute value of the sign of the charge. We don't have to worry about the sign of the charge, so it can't tell us anything about direction. So we do this by right-hand rule. So here's how we do it. So we're going to take our pointer finger of our right hand to make sure you're using your right hand, and the pointer finger points in the direction that the charge is moving, the positive charge, right? And so you might say this charge is moving up. Now, immediately we say, well, that's a bit of a problem. We can't really say up because my up is not the same as your up, right? Up on the plane of the screen is not necessarily the same as up on the paper, something I addressed in day 1 of this, right? If your paper is lying flat and you point flat on your desk and you point the way the charge is moving, you're going to have your fingers pointing away from you, and that's clearly not up. So we're not going to say up. Instead, we're going to say this charge is moving to the top of the screen, right? So with the right hand, your pointer finger points to the top of the screen, or top of the page, I should say, and then you're going to twist your wrist around your pointer finger. Imagine your pointer finger is like an axle, and you can just twist your wrist around it until your other fingers can comfortably curl towards B. In this case, that's to the right of the page. All right, once you do that, then you stick your thumb out, and you have to make an L between your pointer finger and your thumb. That's the way the right-hand rule works. That's the way this cross-product idea works, that there has to be a 90-degree angle between your pointer finger and thumb. And so you stick your thumb out, and you should be getting into the page. So here's a view of me doing it. So here's my pointer finger pointing to the top of the screen. My other fingers here are pointing to the right along the field lines, and I stick my thumb all the way out, and you can see my thumb is sort of jabbing into the screen. And so that's going to be a magnetic force that points into the screen, and we show that with an X. The X is a vector pointing directly away from us. That's directly into your paper, if you're doing it with your paper, or directly into the screen, however you're doing it. If then you want to do it for letter B, well, now all we do is we reorient, so our pointer finger points to the top right-hand corner of our page. So your fingers are pointing that way, and then you curl your fingers to the right, keeping your pointer finger along the velocity. That's really critical that as you do this, you keep your pointer finger along the velocity. If you change that, then you're not going to get the right answer for this. This would be so much easier if we were in class. I could walk around, I could see you doing it, but you just have to, I'll show you a lot of photographs of my hand doing it. You really have to try it on your own to make sure you get it. And we should, again, be getting into the paper. In fact, for letter C, you should be getting into the paper as well. Try it on your own. Make sure you can do it until you get that. What about for letter D? Well, for letter D, the charge is moving to the right, and the field is also pointing to the right. And so no matter how you orient your hand and twist your wrist, you're not going to curl your fingers at all. So there's no preferred direction. And when the angle is 0 degrees anyway, so we're going to get 0. So there's no direction on 0. And so we learned some interesting results here, that if a charge moves directly with the field, it will feel no magnetic force. What about if it moves directly against the field? What angle would that be, right? If the field is pointing to the right and the charge is moving to the left, that's an angle of 180 degrees, right? They're exactly opposed to each other. And what's sine of 180? If you're not sure, you can put it in, but you really should know that at this point. Sine of 180 is 0. And so we see if a charge moves directly against the field, it also does not feel magnetic force. So what we learn here is that a charge has to somehow cut across field lines to feel a magnetic force. If it goes directly with the field or directly against the field, it does not feel a magnetic force. Let's try problem 5. Okay, so I want you to read it, do part A, pause the video as you do, then go back to see how I draw it. Luckily, we have a compass rose here, so we're not making any guesses. All right, so it says the magnetic field points due west, and it's not a guessing game. Look at the actual compass rose, and west is over here, so you have to draw some magnetic field lines pointing to the left. It's always a good idea to draw a bunch of magnetic fields, especially if it says it's a uniform field, right? So draw a bunch of them pointing to the left. But if you do it any other way, I don't know. Maybe you're not thinking, or maybe you don't really know how to read a compass rose. But look, if the west is this way, the magnetic field has to point that way. And then the charge, it says the electron is moving due north, so that's the top of the page here. Like that. And so here's our situation. There's an electron moving due north in a field that points due west. Alright, so for letter B, we want to find magnitude and direction. So magnitude is real easy. We're doing F sub m equals QVB sine theta. It's an electron, so you know what the charge is. If you don't remember, you can look it up. And here's just a matter of putting the numbers in. What's theta going to be? Well, you can clearly see there's a right angle between velocity and field. So we should, in magnitude, be getting 2.1 times 10 to the negative 13th newtons. Alright, you should have no problem getting that. It's clearly a 2 sig fig problem. What about the direction? Well, here's where we do our right-hand rule. So follow along with me. I'm going to show you some photographs of my hand doing this. Okay, so the charge is moving again to the top of the page. So you point your right hand, so your pointer finger and all your fingers are pointing to the top of the page. And now you're going to twist your wrist about your pointer finger until you can comfortably curl the rest of your fingers to the left, because that's the direction of the magnetic field. So in this case, you could stop like so. Sometimes you want to point all your fingers that way. Some students like to point just the middle finger and just curl all the other fingers in. But here's my pointer finger pointing away from me to the top of the page. My middle finger pointing with B. Okay, so did you get that? or did you have some trouble doing this? Because I know some students, when they have their pointer finger pointing away from them, although it's tough to see, then try to curl their fingers to the left in this orientation, so that doesn't work. That doesn't feel right. If you have your pointer finger away from you and you try to curl the rest of your fingers to the left this way, your knuckles won't allow that to happen, right? If you're trying to do something that doesn't feel natural, it's not. So things are definitely going wrong. All right, so we should be in this orientation here with your pointer finger away from you, your middle finger, the other fingers to the left, and then which way is your thumb pointing? Up, right? Wait, no, we're not supposed to use the word up because up is kind of relative, right? If I were doing this on my screen, my thumb would definitely not be pointing up. So what other word did we use? We said out of the page, right? So here we have our thumb pointing out of the page. Except that's not correct. Do you know why it's not right? Did you figure it out? If not, pause the video, see if you can figure it out on your own. It's this. When we talked about the right-hand rule the first time, we said that when we start, our pointer finger has to point in the direction of motion of positive charges, and we're dealing with an electron, which is clearly a negative charge. So what do? Well, we got some options. We could say a negative charge moving to the top of the screen is the same as a positive charge moving to the bottom of the screen, right? So we can sort of flip everything around. So let's try that, right? So we start with our pointer fingers pointing to the bottom of the screen, or bottom of the page. Now, if this is a little tough for you to do, it's sort of like you have to get your hand in front of you and like you're going to jab yourself in the face, you know what you can do? Just turn it around. Just turn your whole paper around the other way so it's nice and easy. And now your pointer finger is going to point to the bottom of the page, like so. And then your other fingers have to curl this way. So you're going to twist your wrist about your pointer finger, like so. So now your middle finger can point the way the magnetic field is pointing. And then you can stick your thumb out. Now you can't quite see it, so here's another view of it. So here's my pointer finger pointing to the bottom of the page. My middle finger pointing this way along the field lines. And then my thumb is, look at this, it's jabbing itself into the page. And this is the correct way to do it. And so our correct direction is down. No, wait, no, we can't say down because that's relative. Instead, we're going to say into the page. Because when you do it, and it's a very physical sort of thing, you've got to make sure you're doing it, you should feel your thumb jabbing the paper. That means that your magnetic force is pointing into the page. And how we show into the page? That's going to be an X, right? Or an X with a circle around it, but the X is the important part. And so here's our answer. Here's magnitude. Here is the direction. One more way to think about it, though, well, you could say change the direction of the velocity. Another way to do it is to change your answer. Just do the right-hand rule like normal. You got the thumb pointing out of the page, and then just say, well, then if it's negative charge, just flip your answer. In this case, it'll be a force into the page, all right? So you can either change the velocity or change your answer, or you can use your... Now, I always like to use my right hand, but if you do use your... It does work. Now, you can't see me. If you were in class, you'd see me mouthing the words left hand. But we don't like to do that, right? It's the right-hand rule, so I always like to do just one thing. I like to always use my right hand, although if you happen to use your left hand, it will work for negative charges, but I don't like to do that. So let's just do it other ways, right? Let's always do it with the right hand and either flip the direction of the velocity or flip your answer, but you got to flip something. But I guess it works. If you want to try it the other way, you will get the right answer. I just don't really like to do that very much. Okay, let's go ahead to... Oh, one more way to think about this, right, is that we're looking down at it and your thumb was pointing into the paper. That was down. I said we shouldn't be using down except for the fact that we are using a compass rose. This literally is a problem where this picture, you must be looking down at it. So if your thumb is poking into the paper, well then it's going to be down. It absolutely will be down. This is one case where you can actually use the word down.